Hello, everyone. Okay, I trust you can hear me. You can hear me. I'm trying to set up the whiteboard because I'm in a slightly unusual location, and I'm trying to set up the whiteboard which I've prepared previously, but somehow I'm showing you a new whiteboard which I don't need. So just give me a minute to sort out the technical issues. By the way, can you hear me well? Please let me know if you can hear me. Okay, perfect. Yeah, I'll switch on my camera in a bit. I just trying to sort out the whiteboard issue. Okay, right. I sort of can't sort it out, so I will have to copy the questions as we go along. I do apologize for that. It's an inconvenience, and I'll try to minimize disruption caused by this. So Zoom. Okay, so welcome to this webinar. Let me just show myself. I think I'm really bad with technology. Okay, sorry. So you can hear me, and I think you can see me. I'm in a weird location, so apologies for that. I'll have to switch off my camera in a bit because my internet is not great. And yeah, so hello everyone, and let's start the session. Yes, there will be a recording for this webinar. It's being recorded at the moment, and I trust the whiteboard is also being recorded. Okay, so I'll stop my video and let's get on with some pulleys. Okay, so today is a year 10 webinar, and the topic is pulleys. Pulleys. And problem one is to describe the different movable pulley and movable pulley. Movable pulley. Okay, so an immovable pulley is a pulley that is fixed to something. For example, it could be fixed to the ceiling, which is typically is. So we have a pulley fixed to the ceiling. So you pull one side of the rope. So you pull, and this is you can use that to lift a load, for example. Yes, load. So that, let's call this effort. Effort. Okay. So if we look closely at the pulley itself, we can see, so this is the pivot, and the effort is this force, this effort, F1, and the load applies a force F2. And if the radius of the pulley is R, then the moment of F1, moment 1 is F1R, and moment 2 is F2R. In order to lift something, the two moments have to be the same. So that means M1 equals M2. And that means F1R is equal to F2R, because R is the same. Then we have F1 equals F2. So the load is equal to the effort. So that's the effort is equal to the load. In other words, to lift a 100 Newton load, you have to apply 100 Newtons. So that's what I'm trying to show here, okay? To lift 100 Newtons, you have to apply 100 Newtons. Now, a movable pulley, so transfers force, transfers the same, yeah. A movable pulley. So what's a movable pulley? Let's say you have, this is the ceiling, and you would normally have this is the effort. So the pulley is here, and the load is attached to it. Load. And this is the effort. Okay, so you're pulling up here, but the load is acting here. The load is attached at the middle of the pulley. Let's look closely at what's happening here. So this point, we can say it's fixed because that is the pivot. Pivot. And this is the radius. So this distance, so that's R, and that's R. And the effort is applied here. Let's call it F effort. And here we have the force of the load. Okay, let's F1. F1 is effort. So, okay, let's be consistent and say this is F1 and this is F2. F1 and F2. F2 is effort and F2 is load. Now, the moments, again, have to be the same. Moment 1 is equal to moment 2. But, so this is the pivot here, because this point is not moving. Because when you pull the rope, this point does not move. This point remains stationary. Therefore, you would M1 is equal to M2. The moment of each force is the same. And the moment of the force F1 is F1 times 2r, because the distance to the pivot is 2r. And here, the moment is F2 times r. R cancels, and we see that F2 is twice effort. So the load, in other words, is 2 times the effort. In other words, if you use a movable pulley to lift 100 Newton load, you only need 50 Newton of force. Does that make sense? Does this explanation make sense to you? Um, it's the same with if the moments are equal, you have rotation at constant speed, just like in Newton's first law, remember? If you have unequal moments, you have accelerating rotation. But if the moments are equal, then you have rotation at constant speed. Just like to have motion at constant speed, you have to have balanced forces. To have rotation at constant speed, you have to have balanced moments. It's a very interesting thing, like rotational kinematics and rotational dynamics. Okay, so going into problem two. Problem two. Um, so we have a pulley. It's a fixed pulley. And we have two masses attached, M1 and M2. And you need to find the acceleration of each mass. Now we know nothing about the masses. Let's just assume. So we'll still have a general solution if we assume that we say without loss of generality, assume that M1 is greater than M2. So that means we still have a general solution, but just to get things going, because we want to know which way the system will move, right? So we just assume that M1 is greater. So that means that M1 accelerates down and M2 accelerates up. Now here, you will always see these phrases. It is a light frictionless pulley, and it's a light inextensible string or rope. So why do we have to say this? Well, if the pulley was heavy, you would need a force to accelerate it, just like you need a force to accelerate anything. So if the pulley had mass, you would need a force to accelerate it. And that would mean that the tensions in two ropes would be different before string, inextensible. Inextensible. So if, and the same for friction, if the pulley had friction, the tensions would be different. The tensions in the two ropes would be different because you need an effort to pull the rope. Third, then otherwise, tension in two ropes would be different. Not two ropes, it's a single rope, two sides of the rope. Two sides of the rope would be different. And it's a light and extensible string. That means you can't stretch it. And if you can't stretch it, that means one end of the rope will always move at the same speed as the other end of the rope, assuming the rope doesn't go slack. And the inextensible part also means that the tension would be the same. So basically, the tension is the same throughout the rope, and the speed of each end of the rope is always the same. And that's an important thing, because if the speed is the same, so is the velocity is the same. Sorry, if the so is the position, the movement, movements are identical. That means accelerations are the same. So this means that acceleration of mass 1 has to equal to acceleration of mass 2. And of course, by modulus, because one is up, one is down. But that's not important. So yeah, now what do we do next is we put acceleration. So the mass m1 accelerates down. So we write Newton's second law for mass m1. So we have m1 g going down, and up we have tension in the rope. Now m1g will be slightly greater than the tension. That's why the system is accelerating downwards. Sorry, downwards. Now Newton's second, we have mass times acceleration is equal to the resultant force. And the resultant force is m1g minus t. So m1a is m1g minus t. So that's the first equation that we got. Now we look at the second mass. Second mass has two forces, m2g and t going up. This time t is greater because because we know that it's accelerating upwards. So we write Newton's second law. Mass 2 times acceleration is equal to tension minus m2g. And here we can express t. T is equal to m2a plus m2g. And we sub that in to the first equation. We sub that into here. And we get m1a equals m1g minus m2a minus m2g. Okay. We take a is the unknown, so we take a to the left. So m1a plus m2a equals m1g minus m2g. Then a, open bracket, m1 plus m2 equals g, m1 minus m2. So acceleration is equal to m1 minus m2 divided by m1 plus m2 g. That's the acceleration of the system. Okay. Yeah, so the question is find A. Let's find T as well. Find the tension in the ropes. Let's look at this solution. So let's check. So if m1 is equal to m2, then acceleration would be, what would the acceleration be if m1 was equal to m2? From the equation, just looking at the expression. 0, yeah. Oh, that makes perfect sense. If they are the same mass, then there would be no acceleration. If m1 is greater than m2, then acceleration is positive. And if m1 is less than m2, then acceleration is negative. That means going the other way, which makes perfect sense. Okay, now let's find the tension. So we know that T, to find the tension, T is M2A plus M2G. So now it's just a bit of a math skill to put this together. So M2 multiplied by M1 minus M2 over M1 plus M2 G plus M2G, and T is equal to G multiplied by, wow, M1 M2 minus M2 squared plus M1 M2 plus M2 squared. Oh, M2 squared cancels. M1 plus M2. So T is equal to G, open bracket. So that's 2 M1 M2 divided by M1 plus M2. Okay, that's it's called a harmonic mean, I believe. Harmonic mean of the two masses twice, 2g times the harmonic mean. Interesting. Anyways, problem 3, which I've prepared for you. Well, problem 3 is quite extensive, so I'll try to do a crazy thing and copy it from Hello, can you still hear me? Apologies. Okay, problem 3. Problem 3. So apologies, something, yeah, something off. And so this is problem 3 that I've prepared for you. This is an A-level question for, right, for mechanics, so for maths. So two particles A and B have mass, m kilogram and 3 kilogram respectively, where m is greater than 3. The particles are connected by a light and extensible string which passes over a smooth fixed pulley. Initially, A is 2.5 meters above horizontal ground. The particles are released from rest with the string taut and the hanging parts of the string vertical, as shown in the figure. After A has been descending for 1.25 seconds, it strikes the ground. Particle A reaches the ground before B has reached the pulley. Okay, so basically the distance from B to the pulley is more than 2.5 meters. Show that the acceleration of B as it ascends is 3.2 meters a second. Okay. So you might be tempted to do the question the same way as as I did the previous one, but actually it's much simpler because they gave you the distance, they gave you the time, so it looks like it's going to be a SUVAT question. So for A, I'm going to try to use SUVAT. So the distance is 2.5 meters. The initial velocity is 0. Final velocity we don't know, and we're not looking for it. Acceleration is what we are looking for, and time is 1.25 seconds. So it looks like we can find acceleration. That's nice. So let's just choose a appropriate equation. So I'm saying it's going to be ut plus 1/2 at squared. And then s is 2.5 meters equals 0 plus 5. Oh, what am I doing? No. Plus 1/2 times acceleration multiplied by 1.25 squared. Okay, so here acceleration is 2 times 2, it's 5 divided by 1.25 squared. And, well, 1.25, that's 5/4, I believe. 5/4, yes, so it's going to be 5 squared times 4 squared, which is 5, that's 16/5, which is 3.2 meters a second squared. Nice. Okay, so we have the acceleration now. The acceleration is 3.2 meters per second squared. By the way, while we're doing this question, you can notice that how much more structured the A-level questions are compared to COMPOS questions, for example. And that's the kind of questions you will get at university, right? Which are not structured, because here they guide you through the solution. B, find the tension in the string as A descends. So we need to find the tension. Okay, so now we actually use dynamics. So we look at the B. We start with B because we know the mass B. And the tension in the rope is T. Now downwards is 3 times G, so 3 times G. And we know that the acceleration is up, and the acceleration is 3.2 meters a second squared. Okay, let me just not do this, not do 3G. Let's make it M2G. And of course that I know that M2 is 3 kilograms. Okay, Newton's second law and mass times acceleration. So M2A is equal to the resultant force, and the resultant force is T minus M2G. And therefore, I can find the tension. Tension is M2A plus M2G. And I know that we can write it M2, A plus G. And that is M2, which is 3 kilograms, multiplied by 10 plus 3.2. Okay, I think they were. I think they were. They wanted you to use 9.8. Yeah, let's do 9.8. 9.8, because then you get a beautiful number. 9.8 plus 3.2, that is 13. 3 times 13 is 39 newtons. Nice. Next question, C. Show that M is 65 over 11. C. So now we consider this second mass, so A. Now there's a tension going up, and we know that it is 39 newtons. We have M1G, and we know that the acceleration is down, and it is 3.2 meters per second squared. So we write Newton's second law again, like nothing new. Newton's second law says that mass m1 times acceleration is the resultant force, which is mg minus t. And what are we looking for? Oh, we're looking for m1. M1, open bracket, G minus A is equal to tension. I'm just rearranging it. And here you have M1. It's equal to tension divided by G minus A, which is equal to 39 newtons divided by 9.8 minus 3.2. And that is, what is that? 9.8 minus 3.2, that's 6.6. 6.6, 39 divided by 6.6. It's meters per second squared. Newtons, meters per second squared. 390 over 66. Can I divide by something? Can I divide by 2? That's oh, we can divide by 3, of course. So that would be 22. And that would be 130. And I can divide by 2, so that's 65 over 11. Somehow dividing by 390 by 3 is easier than dividing by 2. Okay, anyways, that's kilograms, of course. And I think that's what they wanted. State how you have used the information that this string is inextensible. Well, because the accelerations are the same. And because imagine if you could stretch the spring, right? That means one mass could move faster than the other. But that can't happen. So I've used it by saying that A1 is equal to A2. And that is only possible because the string is inextensible. Okay. Finally, I get find the time between the instant A strikes the ground and the instant when string becomes taut again. Okay, this is not really a question about this is not really a question of pulleys. Let me just talk you through this. Yeah, let's do it. I mean, come on. So E. So you have A is on the ground. We have a situation. A has just hit the ground. Just hit the ground. Well, when it hit the ground, it was moving at a reasonably high velocity. That means B is also moving. B is moving with the speed A had just before the collision. Let's call that speed u. So u is the speed of A as it hit the ground. Okay, so just before it hit the ground, it had speed u. And B, that means the rope goes slack. Rope goes slack. Slack. And that means B will go up for some time. B would like that. And when B reaches the point where it started, the rope won't become taut again. So let's call this point, um, call this point P. When rope becomes taut, when B comes back to point P. Okay, lovely. So we need a seed of we need to find workout U. So workout U. We know that A was in motion for 1.25 seconds. So that's a suvat. Suvat. We know the time is 1.25. Initial velocity was 0. That's when as A fell. S is 2.5. And final velocity is question mark. You know what? We know the acceleration is 3.2 meters per second squared. So it actually use V is equal to U plus 8. So V is 0 plus hello. Right, lovely. The whiteboard has erased itself. Well, okay. Well, we'll have to move on. I do apologize for technical issues today. Okay, so moving on to next question, and uh, Okay, so the next one is problem 4. It was supposed to be problem 5, but yeah, problem 4. In problem 4, so you have a ceiling, and you have pulleys. One is like this, one is like this, one is like this, rope is like this, rope is like this. So you have mass 2 attached to this movable pulley, and mass and acceleration of each pulley. Oh, sorry, of each mass. Find A1 and A2, and find the tension in the rope. Okay. So what can we do? Well, let's just assume that M1 is greater than M2. So without loss of generality, we just assume M1 is greater than M2. That means M1 is accelerating downwards. The acceleration is A1. And M2 is accelerating upwards. And the acceleration is A2. Now, these accelerations would be different because they're not attached to the same rope. Okay, the two masses are not attached to the same rope, so they would be different. And let's try to work out, well, let's try to work out a link between the two accelerations. What is the link? Is the link between A1 and A2? Well, you can imagine quite easily that if you move M1 down, so imagine I move M1 by x1 centimeters. So move M1 by x1 centimeters. That means that this end of the pulley also moves up by x1. x1. This point on the rope remains stationary, so it doesn't move at all. Whereas the middle section, if you draw a triangle, the middle section moves up by a distance. How much? How much does the middle move up? x1 over 2, well done. Point A moves by x1. Okay, point C is of course it's not stationary, but for small disturbance, if x is small enough, we can say that C is stationary. Point C is stationary. and point B moves up by x1 over 2. Yeah, so this is x1 over 2. Exactly. So mass m2 moves half the distance m1 moves. And that's what we spoke about this in the previous in problem 1. In other words, that x2 is equal to 1/2 of x1. Now, if we differentiate this with respect to time, that means that velocity 2 is 1/2 of the velocity 1. And if we differentiate that again, don't worry if you're not following the differentiation bit. That means acceleration 2 is also 1/2 of acceleration 1. Sorry. All right. Ta-da! We got an important result. So here we differentiate. Even if you don't know how to differentiate, which I'm not expecting you to know how to differentiate, but even if you don't know you understand that if the displacement is double, that means the speed is double, and that means the acceleration is double as well. Okay. So we got this expression connecting A1 and A2, and now we just need to write Newton's second law. So Newton's second law for mass m1, so m1, we have the tension, and we have m1g, and it's accelerating downwards at acceleration a1, and therefore we can write that m1 a1 is equal to m1g minus t. Okay, so now the second mass, m2, we have m2g. Now, this is a question mark because it's not tension, it's a different rope, right? So let's look at the block, at the pulley, at the movable pulley. We have two ropes attached at either ends. And we know that the tension in this pulley is T. The downwards pull, that's the tension in this string. So what am I talking about? So we're talking about this this pulley, and we have two ropes pulling it up and one rope pulling it down. But because the mass of this pulley is 0, it's massless, that means this has to be 2t effectively. Right, so because the m0 is 0, so m0 times acceleration is equal to 2t minus, let's call it x, and because the mass is 0, so 0 equals 2t minus x, so x is 2t. Okay, so this is 2t. So the force pulling the mass m2 up is actually 2t, it's twice. And that's what we did in the first question. We said that the load is twice the effort. And that's why it's 2t here. And we just write Newton's second law. So it's accelerating up, and acceleration is a2. m2 a2 is equal to 2t minus m2g. All right, so we got three equations, 1, 2, 3. We have three unknowns, a1, a2, and t. And I think we're good to go because we have everything we need. So let's make t the subject from 2. So from 2, I write T equals M1G minus M1A1. And I sub that into 3. And I get M2A2 equals 2M1G minus 2M1A1 minus M2G. And now I use A1 is 2A2. A1 is 2A2, yes, I can sub that in. So I sub 1 into, so M2A2 equals 2M1G minus 2M1 times 2A2 minus M2G. So now I have only one unknown, which is A2, and I can sub that, well, I can express that out. So this is, I take this to the left, so 4M1A2 plus M2A2 equals 2M1G minus M1G, and then acceleration A2 is 2, that's M2G, M1 minus M2 G over 4M1 plus M2. So that's the acceleration of the second mass. And let's just confirm if M2 is equal to 2M1, if the ratio of the masses is 2, then acceleration is 0. Well, that makes perfect sense. So if the second mass is twice the first mass, then they would be stationary. Well, not necessarily stationary. They would not be accelerating. So if m1 is greater than 1/2 m2, then acceleration would be positive. And if m1 is less than half of m2, then acceleration would be negative, which makes perfect sense. Okay, so A1 is just twice A2. So I'm not gonna just double it. Come on, easy. And then to find the tension, you just sub that into any of the equations. So tension is equal to M1 G minus M1 A1, which is, well, A1, which you found in the previous one. Okay, I'm a bit too lazy to do this right now, but I hope you got the gist. So bottom line is you write, you figure out how the accelerations of the particles are related. Usually they're the same, or they're different by a factor of 2. So let's compare what we did before. So in the previous question, we had M1 and M2, and they were connected by a fixed pulley. And we knew that acceleration A1 is equal to A2. So one is accelerating up, one is accelerating down. And then we worked out the acceleration. And the acceleration was m1 minus m2 divided by m1 plus m2 g. So quite neat. And the tension was 2 m1 m2 divided by m1 plus m2 g. So quite interesting. Now here got a different scenario. You have two masses. One is accelerating down, one is accelerating up. You know that the ratio of accelerations is 2 to 1 because one is connected to a fixed pulley, one is connected to a movable pulley. And you use that fact. So you use this fact here. Then you have the Newton's second law and Newton's second law again. You have three equations, three unknowns, you solve it. This is how you do physics, okay? You write down a physical law in mathematical terms, you write another one, you write another one, and you keep doing that until you have three, three, three unknowns and three equations, or four unknowns, four equations, or whatever. That's yeah, nice. So once you can solve it using maths. Okay, let me see what else I have prepared for you. Okay, I'll do one more problem today. So problem 5, which was supposed to be problem 7. Problem 5. So I love this one because this is very interesting from the point of view of physics. Hard to get your head around. So you have two masses, one on top of the other, small m, big M. They're connected to a pulley. Okay. The floor is smooth. So floor is smooth. Smooth. The coefficient of friction between the top and the bottom block is 0.5 between blocks. Blocks. And we pull the bottom block with a force F. Such that the bottom block accelerates with acceleration of g/2. And what you need to find is the force F. What is the force needed to pull the bottom block to the right such that the acceleration of that block is g/2? And we know that small m is 1 kilogram and big M is 2 kilograms. Okay. We start by, well, we start by realizing that the acceleration would be the same. They're connected by a light inextensible string that over a fixed pulley. That means that they have the same acceleration. So first, both masses have the same acceleration. That means A1 is equal to A2. Secondly, I write the top block. Top block. There's a full force to the left, which is the tension force. There's a friction force here, friction force. And there's a normal reaction force, of course, normal reaction, and there's gravitational force down. This is mg, and this is friction force. So we can safely say that, well, friction force we know, because it will be sliding, it will be accelerating, it's mu n. We know that. And that means that n is equal to mg, so vertically the forces have to be balanced. And then horizontally, so in the y direction, in the x direction, it's accelerating to the left. So that means mass acceleration is equal to the resultant force. So that's T minus mu n. But n is mg, so we can rewrite this ma equals T minus mu mg. Nice. And then 3, bottom block. Okay. So there is mg, there is normal reaction force. It's a different normal reaction force. And now there's a tension in the rope here. We're pulling it with a force F. And there's the friction force. Which way is the friction force? There's no friction with the floor, but there is friction with the top block. Leftwards, correct. It's the Newton's third law pair of this friction force. So because Newton's third law, if one object pushes another, the other pushes the first one. That means if the lower block pushes the top block to the right, that means the top block pushes the bottom block to the left. So, and that force is also mu n, so these forces are pairs. These are Newton third law. Okay, so one is pushing the top is pushing the bottom and the bottom is pushing the top. And now we can write down Newton's second law. So horizontally in the x direction. So we know that it is accelerating to the right. So we can say mass times acceleration is equal to the resultant force, which is F minus T minus mu n, which is mu mg. Nice. So now I can express T from here. T is equal to ma plus mu mg. I sub that into here and I get ma equals F minus ma minus mu mg minus mu mg, and I get F is equal to mass times acceleration plus mass times acceleration plus 2 mu mg. Excellent. And now I just substitute because I know everything. So F is going to be F is going to be 2 multiplied by g over 2, because we know A is g over 2, plus m, which is 1 kilogram, multiplied by g over 2, plus 2 times 1/2 times 1 times g. I'm just going to give the answer in terms of g. I mean, that is perfectly reasonable. G over 2, this cancels. G plus g over 2 plus g 2g plus g over 2, that is 5g over 2. All right, that is the answer. Okay. Is there anything else? Oh, nothing. Nothing of interest. So I'll stop sharing and right. Okay, I hope that was useful, and it's good to be back. And I'll see you all in a week's time. So next week we're doing maths, and I'll finish here. Was there any questions? All right. Okay. All right. All right. You're welcome. See you.